a zip file directory. So if you have PTW32 on your computer, then please open it up and see if you can run it. But before that, let me look at the, so here is our roster. So today is class lecture number 21. 1, 2, 3, 4, 5, 6, 7. So we still have good 9 classes to go. So plenty of time to do interesting things. Okay. So here we are. We have had, let's see, 27, yeah, perfect attendance the last 3 classes. So let's see how it goes today. Let's look at the attendance right now. So now it's low, 18. So a little bit more. Will you please turn on your webcam, Andrew, Cassandra, Asael, Ricardo?
Yeah, I'm trying to connect to my webcam through my phone. It's just that Blackboard isn't working on my phone, so I'm just trying to set it up.
So are you at your home, Asael? Or
Yes,
you are...
I'm on my computer. I just don't have a webcam connected to my computer. So I'm going to connect to my phone. It's going to take a while.
Professor, where exactly is the zip file for homework 17? Because I don't see it in the course materials tab.
Really? Okay, let's look at it.
I found it in the PTW Power Tools section.
That's right. So I made a mistake. I told you I wrote course materials, but it's not course material. There is a PTW32 section on the, so that's where they are.
Yeah, I found it. Thank you.
Right here. Okay, so this is a motor simulation, right? So you need to open that, and also you need to open from assignments. Let's see. On your view of assignments, this is what you see. Yeah, okay. So then you need also to open this document, 17S motor simulations versus version 2. So then let me show you the
Dr. Ramos, we can't see your screen.
Oh, sorry. I'm sorry. I forgot to share. Do you know?
Yes.
So you need to open also this. This is the template to respond to the homework. I'm trying to drag that.
Could you show us what it should look like on PTW once we
No,
Open the example.
on PTW 32, this is how it should look.
Is that after we run it?
So you need to go to open project, open. And then when you open, you need to go to the routing of, and then you'll find exercise 3. And then this is an it's an application or an executable PRJ. So when you open this, it should look like this. So what happened? Document. It did not cancel, so project open. Right there.
Mine opens a component editor. I don't know why.
Yeah, that's what mine does as well.
It doesn't open this
No, it opens a component editor.
component editor. Okay, so that's this file here. So then now let's. Okay, so then go to documents and then click on the one line. Does it work?
Yeah. Yeah, it just it says 1 line 001, and that's what we open.
Okay, so here I have drag into your view the homework template. So this is also, so let's do this homework, okay? So it says in the one line diagram, I think I have this here. So I'll put this on the other camera. I put this on this camera. Right there. Okay, so we want, so in this one line diagram from bus number 2 here, which is at 480 volts. You see the 480 volts here? Bus number 2. So have you been able to open the PTW 32?
Yes.
How many? Let's ask by chat.
No, I'm still having trouble. It says that file must exist in the project directory, but I think I added it to the already.
chat. Yes, yes, okay. You still not too many. 1, 2, 3. Ethan, Santos, Hugo, Sergio, Jesus, Israel, Marco. So right, yes, if you can open PTW 32. Julio, Ray, Asael. Okay, Asael, you got it?
Yes, I got it.
Great. Okay. So first, look at the boost here. This is the low voltage boost. And then this is the medium voltage boost at 12,000. And then this is at 480. Now, so there are three circuits in the low voltage boost. The first one goes to a panel board, which is going to be lighting panel board. The middle one at the center goes to a motor, and the one on the right goes to a capacitor. So this is a power factor correction. Okay, now what we want to do now is to open and close these switches, these circuit breakers. So let's see how we can do that. So let me share the screen again. Excuse me a second. Okay, so right now this, for example, on the left-hand side circuit breaker, right click on it, and then we can put in service, out of service. So let me see if I can change. Oops, no. Okay, first I need to select, left click. Once it's selected, right click. Okay, now it's available. Disconnect, so I put it in service now. So now it's in service. Okay. So then what we want to is run the motor on itself, okay? So then it's already selected, right click, out of service. Okay. So then, so we have this network. See the utility data, 12,500 volts. The LF, I don't remember what LF means, line to line fault. No, I don't remember what LF means right now. Voltage angle, LF kilowatt, LF K bar, okay. So this is a lot of information here. All right, so then, and then we have this transformer, delta Y transformer. So if we click on the transformer, and then we go to components, so what is it? No, that's where we look at transformers. No, okay. At the bottom, it's a motor, 60 HP. CBL means cable 02. So that's the only cable in the, so for example, how can I read the data of this cable? If I click on it, that's the name. I want to see the data. If I click on the symbol, yeah, right. So I can open this dialog. So cable. So for example, what is the length of the cable? What is the size? What is the length of cable is 200 feet. According to according to here, it should be 300 feet right here. 300 feet. So let's put here 300 feet, okay? 300. Then it's cable size number 2. So cable size here, look. Okay, number 2. However, there are question marks there because we will look at the voltage drop and see if that cable is good enough to be within the voltage drop, okay? So then we see that's cable, then impedance. So here are the impedances. So what is the impedance? For example, on a base temperature, short circuit include. So here is the impedance. Look, R in units of ohm per 1,000 feet. Positive sequence, 0.2 ohms, 0.05 X. Okay. Then ampacity selection. It's a 90 degrees cable. The ambient temperature is 30 centigrade. Ampacity calculation, let's see, what's the ampacity? The design ampacity here is 130 amps. And the ampacity calculation, what would it be? I don't have any result. Okay. Fine. So then let me close this. So that's cable. Now let's look at the motor. So then the motor has also a component editor. So it's an induction motor rated 460 volts, 60 HP, 80% power factor lag. The starting power factor, efficiency 93%, LRA over FLA 6.5. So these A's are amperes, okay? So these are currents, the ratio of the locked rotor to the full load Okay, so lock rotor is the denomination that is given to the condition of the motor when it starts. So when it starts, the motor is not moving as if it were locked. However, and then it will draw a current which is 6.5 times higher than the full load current. The full load current is the current drawn by the motor once it's in steady state. Okay, so where would that current be? Do we see anything for that? No, I don't. Running. We need to go to the table. For example, let me open the book. Let me open the book here. The last chapter we were looking at is chapter 13, I think. Okay, 13. Right here. So we are talking about this motor, induction type, 460. How many? 60, 73, 77 amps. So the minimum ampacity of the circuit for 77, let me calculate here. The minimum ampacity of the circuit is going to be 77, which is this number here, times 1.25. So that's 96 amps, okay? That's the minimum ampacity of the circuit. So then, now let me go to chapter 11 and look at the cables to this. And then we need to find an ampacity for the cable of 90 degrees. So this is this column here, 90 degrees. And then find 96 amps. So let's find 96 amps here. Right there. That's 95 amps. Almost 96. And what cable is that? The AWG is, it says number. Oops. No, it's got to be 100. Hold on. It's got to be here. 90. Okay, 95, right there. Number 4. Number 4. Now, we have suggested number 2, which is good for 35 more amps. Why could that be? Because of the voltage drop. It's a long cable. Cable we said is how many feet? 300? Okay, so then the simulation will tell us if we are under the voltage drop or not. Okay. So then what else? What else can we look at? Well, that's the cable, the motor, the transformer, So transformer is 75 kVA, delta Y. Okay. So now, so let's run, okay? Let's run. And then, so then run here. And then the balance system studies. Okay, so then we have this dialog box. And then I have clicked on, we want to see demand load. We want to see low flow. And we want to see short circuit. And then each of these, there is going to be a report generated in the current directory that we have, we are using in your computer. The current directory, there is going to be a created report file for DL, demand load, another one for LF, and short circuit RPT. So these are text. Okay, so then we run. And then the message is no errors. Are you getting no errors? Okay. So I don't have any errors, system, everything, ta, 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 ta. Okay, so I close. Okay, and now I need to complete this table. DL, the load summary. Okay, so then I need to go to my directory path right here. And this is my path on top. Okay. And then here is the DL. RPT report file. So I right click on it. And then I'd say open with, what is it? I need to first select, right click on it. Open with here. No path. Okay. So here is the report. Okay, now, since the report is lengthy, I put a screen on the report, and we only want to get the load summary, total load summary. So then look at the, read the heading of the table, and then find this heading on the report. So here is load summary, but I need total report load summary. So that's not it. See, there are many information for different buses. Bus 01, bus 02, bus 03, bus 06. So here is the load summary at the end. Then total source load summary. So total source load summary, okay? Good. So now let's do connected load. The largest is the motor. So it's at 48.1. KVR 36.1. KVA 60.2. And then the total loads is the same, right? Total loads is the same. And then 80% power factor. Here is 80. So 36.1 square over 48.1. The inverse tangent. And then the cosine. 80% indeed. I just calculated the power factor from using this and that. I did tan theta equals 36.1 over 48.1. And then I calculated, once I got it theta, I did cosine theta. So here we get theta. And then cosine theta 0.8. Okay. So that's this part. So now let's move to the second part. LF. So now we need to open the second report, which is low flow. And here, look, here we are going to look at the voltage drop. Okay, so then let's open the second. So then again, go to your, in your computer, the directory path. Then locate LF, low flow here, right here. And this is it. Okay, so the date is correct. March branch voltage, so here are the criteria for branch and total. So branches, that would be the voltage drop in this section. That's branch. Well, in this case, it would be the same as total. Well, I don't know if it says after the transformer. Well, here is only one circuit, so I think branch and total are the same here. Okay. Utility impedance, yes. Transformers phase shift, no. LTC line tap transformer, line tap changer transformer, calculation method, net Newton. PU values are expressed on a 100 MVA base, very large base. Okay, so So the voltage at the generator is 1 per unit. Boost voltage convergency criteria. Okay, balance voltage drop. Okay, balance voltage drop. So what do we have to look at? We need to look at balance voltage drop and load flow analysis. This table. So this is it, okay? But we don't want to do the utility, no? Balance voltage drop, the PV source. What's PV? Balance voltage. Okay, so here is boost number 1, boost number 2. So where are we? So this is boost number 2. And then what's under boost number 2, further ahead from boost number 2 is the motor. Boost number 3, where is that? Is that a virtual boost? I don't see a boost number 3. Maybe, I think it
The bottom left-hand side.
the motor?
No, bus number 3 is on an open circuit.
Okay, so that's the lighting. Yes. Okay, here is number 3. So we don't care about 3. We care about 2. But then I have the doubt. What beyond number 2 is the motor. So so let's see boost number 2. See, there is a boost number 6 here, which is cable. Okay, cable. So then there is a virtual boost, which is number 6. Can you find boost number 6 in your one-line diagram? Or maybe you can open components and then in components, see if you can find cable is connected between what boosts. I suspect is boost number 6 that we really need to look at. So let's see. Load to boost number 6. That's the cable. Feeder amp 77. Voltage drop 8%. Is very high. Is that 8% here? Or no? Percent voltage drop 1.65. So 8 is the amount of volts. So that may be okay on a 460. And then the percent is 1.65. So it looks fine. It looks fine. So what should I write here? DL. So here we have boost 1. You can put boost 01, boost 02. No, sorry. Boost 0T, boost 06. Design volts. So for boost 06, design volt is 480, boost 02 to, okay. So this may be written like this, perhaps. When we talk about a voltage drop, then we must specify the segment. So then this makes sense from 02 to 06. So then the design is 480. The boost volt is 458. We can see that there. The voltage drop is 4.6. That's high, isn't it? It says 4.6% here. And then we further have another one, load to cable, feed amps. So this is what I was writing here. And then to load on cable. So then here I have another, here I have 1.65. Okay. Percent voltage drop, boost 02. Losses through feeder. Then we see losses. And then load from boost 001 to. Okay. So that's, and then there are questions here. Does the rule voltage less is complied? Okay, so I'd say yes. What is the gauge of the motor feeder conductors? So right now we have number 2, WAG. How many feet long is this motor feeder? So we got 300. If you had answered no to question 1, what is the solution? So if the voltage drop is higher than 5%, then the solution is to change the cable AWG. So we would need to go to the one line diagram and double click on cable to open the component dialog and change to From number 2, we can change to a thicker cable, probably 1 knot. Okay, fine. So let me ask. Okay, so look, let me say the following. If you want to invest time on learning more about this software, remember that in here, PTW Power Tools, we have a tutorial and a guide. So if you want to get a better grade and get some extra points, then any contributions that you make here, I'll take it into account. Okay, so for example, something that may be possible is to have a better interpretation of all these text files. Okay, so for example, I have this question here. Where is bus number 6? We don't see it here. Do you?
No.
So is that this point? Look, there is a point here. So, I found it. So that's bus number 6. It's a virtual books. Okay, so I'll get the extra points in this case, okay? So that means that it's at the end of the cable, right where the motor is connected. Okay. So it seems like this bus is created automatically whenever we insert the motor at the end of cable without creating the actual bus. The actual bus look like the thick lines. All right. Okay, so then now we need to go to the following SC, short circuit. Okay, so then, so the first question is, where is the short circuit going to occur? We can have a short circuit at the bus 1 or at the bus 2 or at the bus 6. So then different short circuit contributions are going to happen because, see, the thing that is limiting the short circuit is the distributed resistance. See, for example, for short circuit studies, we have not done that yet, short circuit studies. This is kind of new material. So for example, here in our network, we have this, then we have the utility bus, and then we have the transformer, and then we have the low voltage bus. Then we have the cable. I'm not putting, okay, well, so now there is another breaker here. Then the impedance. Then there's this virtual bus, and then the motor. Okay. So virtual bus. Okay. So then imagine we have a short circuit right here. So here I'm going to represent a fault like this to ground. So see here, there are utility impedance, C utility, transformer impedance, CTR, cable impedance, cable impedance. So the total impedance is C utility plus C transformer plus C cable. So then we can produce a Thevenin diagram. And then here is the load, the motor, okay, load. At the end. And then we short circuit here. So then the idea is calculate the short circuit current. So this is the B Thevenin. And then this is the C Thevenin. So the C Thevenin is all that sum. Okay, so then we can do that as this. Right. Therefore, as we can see, there are going to be different fault currents depending on the bus which is faulted. Okay. So the highest current will be in the utility bus because that is the one that has less impedance in the trajectory of the fault current. Okay. All right. So let's open the now short circuit. So this is this file here. Then for short circuit, let's see, what are we going to do? Right here. Short circuit analysis data from fault analysis summary. Then we have the bus. Okay, so short circuit, merge 31. All information presented is for review. Okay. Bus name, the utility. Pre-fault. So look, these are the voltages pre-fault. So 12,500 and 480 volts. That's because of the transformer. And then we have fault analysis report. So fault type, three-phase, motor induction, model induction motor contribution. Yes. Okay, so then what's that point? So that point is that when there is a fault, the motor is also going to contribute to the fault. So when there is a fault, for example, here, this is a sink of energy. So all energy, all sources which store energy send current to the fault. So that's the utility through the transformer and the cable. But the motor also has store energy because it's spinning. So when that happens, the motor turns into a generator and it pumps current into the fault. So that's surprising, but it happens. So then the motor contribution is taken into account, the transformer, the phase, etc. Okay, so then we have boost 01. And then there are a lot of, look, the Thevenin equivalent voltage, the Thevenin impedance, the initial initially symmetric RMS fault current. Remember that when we talk about in chapter 7, symmetric and asymmetric. So here are these two topics here, symmetric and asymmetric. Remember that. Let me show you the schematic, the plot. What is that? Chapter 6. So this is what they mean here. This is the symmetric after the transient, okay? And the asymmetric is the peak right on the transient. So the asymmetric can be about 1.7 higher than the symmetric. Okay, so then that depends on the XR, the ratio of inductance to resistance. So we are looking for, again, short circuit analysis data from summary. Fault analysis report. So lots of numbers. The deluge. Summary here. Okay. So it says boost 1 and boost 2. So 12,500, 480, three phase, and then here are the fault currents. 1,169, 1,987.3. XR. This is the ratio of reactance to resistance. So this is related to the time constant. So if XR is very long, the time constant is long. Okay, so this is 7.9 and 2.3. Then line to ground. So this is the first short circuit, a three-phase voltage. And then the second one is line to ground 8, 34.9, 2.1. Okay. Give me a moment. So then we have questions. What is the three-phase short circuit power? Short circuit power. Then there is a formula here, okay? So this is the user formula, usual, square root of 3, B line to line, times I line. I played with the prefixes, so I have megavolts, kilovolts, and kiloamps. So that's fine. And then on the medium voltage boost, on the 480 volt boost, so here is going to be the square root of 3. So Q5 is going to be a square root of 3. 480. And then the three-phase right here, 198, like that. And then we divide that over 1, 10 to the 6. Because here this be, okay. So then that's this amount. The square root of 3 times 0.48 times 1.987. So this is 1.65. And the second one, so now let me put that in kilovolts. So that's 12.5 in kiloamperes. $1.17. So 3 times 12.5 times 1.17. 2533. Look, a lot of power in the short circuit at the boost on the top. On the top, the medium voltage boost. It makes sense. There is only this impedance limiting the short circuit. Okay, so here, this is the case for a fault right here. So that's why we have different short circuit levels. Okay. So this is homework 2, or I mean this homework. Let me see. So now finally, let me go back to this. So okay, so there are two we need to do in the future studies. So let me put here a note. Future work. So one, we said continue reading textbook. Now number 2, this is okay. So we have a panel board in PTW 32. Panel board SCH001. And number 3, short circuit studies. Short circuit studies. beyond report file, which was the file that we finished a moment ago, SC. So read the you can read the tutorial. There's a big chapter on short circuit studies. Okay, so now look, let me double click here on this. So this is a panel board and it has a schedule. The panel here, look. 01, 028, 03, 04, 05, 0. See, here we have put circuit breakers in each of these panels, 07, 8, oh, it's three-phase. It's three-phase because I can see A, B, C. Okay, so 01 and 02 are on A, 03 and 04 are on phase B, 05 and 06 are on phase C. And then look at the bottom. At the bottom, we say 6.7 amps, 7.5 amps, 6.7 amps. So that's the, that reminds me of this. Let me show you this. In chapter 12, we studied this in chapter 12. So see here, 1 and 2 on A, 3 and 4 on B, 5 and 6 on C, and then at the bottom, A, B, C. So that's exactly what we have here. So there is going to be a homework. I'm going to post some notes so that we can upload in one of these breakers a number of luminaires, and then of course we need to know how many amps the luminaire must take. So it's going to be interesting. So let me see if I have that here. Just a moment. I made, let's see. Yeah, luminary schedule. So here, let me bring this one, this. I'm sorry, I need to stop sharing and share again. So just a moment. We are almost at the end, but okay. Luminary schedule. So now drag, okay, so share again. So one moment, please. We are about to go. So luminaires, description of luminaire, the watts, instructions to field table, write the model of the luminaire. So where is the luminaire? I need to put a diagram here with the luminaire voltage. Okay, so all this information is intended to be used in the programming of this schedule, okay? And then once we put that schedule, we will close the circuit here. close, in service now. Now it's in service. And then, very good. So that's the future, okay? Thank you all. See you next Monday. Let me please please turn on your webcams before we go and say goodbye until next Monday. Thank you. Oops, I need to put my webcam.